Hello, my name is Eduardo and this is my video lab report for Lab 3 for Physics 2211. In this lab, we're going to be seeing the effects of the gravitational force in the motion of stars, black holes, planets, and starships, and their orbits. We're going to be using this formula for the magnitude of the gravitational force, which involves the universal gravitational constant, the masses of both bodies, and the distance between them. When we talk about the gravitational force, we always see two opposite forces of equal magnitude that make both bodies affected by it move toward each other. Now, when we talk about orbits, due to the initial condition of a tangent velocity, the bodies don't actually bump into each other and actually move around the center of mass of the system. And in the experiments we're going to be seeing, since the black hole is so much more massive than the other bodies in question, we're going to disconsider its movement completely. Now, I talked about the system, but what is the system? In the first part of the lab, the system is made only by a black hole and a star. But in the second part, we're gonna see instead of a star, a planet and a starship, which are gonna try to make escape the orbit it's stuck in. This is my code for the first part of the lab. Here I use a time interval of 1 day between each imported data point. And when we scroll down here, we can see how I made the simulation work. I just get the initial and final velocities of each time step, multiply by the star's mass and calculate the respective momentums, find the difference between them, and with that calculate the rate of change of the momentum. With that, I can find the perpendicular and parallel components of the net force, draw the respective arrows, and using the formula for the gravitational force, I can estimate the mass of the black hole at each timestamp, and by the end, simply get the average. But what does that actually mean? The net force is exactly the same thing as the rate of change of momentum. So if I have one, I have the other, and that's why I can make this kind of approximation. Here we can see the simulation running. And this is the value we're going to use for the mass of the black hole in the next step. In the second part of the lab, we're going to use the concepts of potential gravitational energy and kinetic energy, both of which are given in the formulas in the screen. And we're also going to be using the fact that the sum of these two, the total amount of energy in the system, is always conserved when the system is isolated, which is the case in this experiment. When the total energy is negative, the resulting orbit is going to be an ellipse, and therefore the ship cannot escape the black hole. Otherwise, it's going to be either a parabola or a hyperbola, and so the ship can escape. We're going to try to find a way for the ship to have a parabola as its orbit, since it requires the least amount of kinetic energy to have a counter effect in the gravitational energy and make us reach zero total energy. Here's my code for the second part of the lab. Here we can see the mass we obtained in the first part for the black hole, and I use a time period of 2 hours for the simulation because it allows me to see the full orbit of the planet and I think it looks nicer. Here we can see how I calculated the ship's velocity. Since we want the total energy to be zero, the magnitude of the kinetic energy has to be equal to the magnitude of the potential energy, and here's how I did that. Then, since the planet is moving too, we need the y velocity of the ship to be at least the same as the planet's speed. So this is the equivalent kinetic energy for that. And that's how I found the kinetic energy for the x direction, just taking that from the total energy. Then I just got the corresponding velocities for each direction and added that to the velocity vector. Here in the calculation loop, we can see the effects of that. Um, I first get the forces of the black hole and the ship on the planet and fight the net force on the planet, and do the same thing for the ship. Use those forces to update their velocities and these velocities to update their positions, and just update the time from then on. And here's how the simulation looks. We can see that the ship kind of went close to the black hole, but we can't actually get closer because we would need a smaller y velocity, and that's impossible since the planet is moving too, and we need at least that amount of y velocity to escape the planet itself. But what if, instead of just taking a quick look, we wanted to stick around? For that, we would just need to reduce the amount of kinetic energy, because then the magnitude of the potential energy would be greater, and therefore the total energy would be negative, and the orbit would be an ellipse, which makes the ship stuck to the black hole. So I just use this constant to lower the amount of kinetic energy, and now let's see what happens. You see, it's a closed orbit. I actually used 20 hours here because 2 wasn't enough for the whole orbit. In conclusion, we can see how big the changing effect of the gravitational force is depending on the initial conditions. And there aren't actually any sources of error in this experiment besides the limitations of the iterative method of simulation. Thank you.